Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering. I'm here to discuss you on the subject non-destructive evaluation and testing. The subject code is ME419, unit number 2, lecture number 13 in the series. And today's topic are sources of high energy radiation, con- controlling radiation exposure, radiation detectors, and safety controls. So today's learning objective are just to provide the students with a basic understanding of sources of high energy radiation, controlling radiation exposure, and to know about radiation detectors, safety controls. And after the lecture, the learning outcome will be the students will have an understanding of sources of high energy radiation, controlling radiation exposure, and students will understand various factors influencing radiation detectors and safety controls. So let's start off with the first topic, sources of high energy radiation. As you can see in the diagram on the right hand side, it is clearly shown the various divisions in which various sources are there of radiation. Like radon has 54%, others have less than cosmic have 8%, terrestrial has 8%, internal has 11%, medical access has 11%, nuclear medicines have 4%, consumer products have 3%, others have less than 1. So others are greater than 1%. So there are different types of sources. So we are discussing about that. There are many sources of harmful high energy radiation, like industrial radiographers are mainly concerned with exposure from X-ray generators and radioactive isotopes. However, it is important to understand that 80% of human exposure come from natural sources such as radon gas, outer space, rocks, and soil and human body. 80% of human exposure come from natural sources. The remaining 20% comes from man-made radiation sources such as those used in medical and dental diagnostic procedures. Okay, normally man-made radiations are used for diagnostic procedures. Okay, in either in medical reasons or in diagnostic procedures. So we have an application. So one source of natural radiation is cosmic radiation. The Earth and all living things on it are constantly being bombarded by radiation from space. Okay. Now the sun and the stars they emit electromagnetic radiation of all wavelengths. So the dose from cosmic radiations varies in different parts of the world due to the difference in elevation and impacts of the Earth's magnetic field. See how they affect. Okay. Now the radioactive materials are also found throughout the nature when they occur naturally in soil, water, plants, and animals. Okay, so the major isotopes for concern that we also previously studied that there are some major isotopes and we have studied the term terrestrial radiation. So here again this one is coming. The major isotopes for concern for terrestrial radiation are uranium and the decay products of uranium such as thorium, radium and radon. You can see that these terrestrial radiations caused due to this uranium and decay process of this are also a great point of concern. Low levels of uranium, thorium, and their decay products are found everywhere. Some of these materials are indigested with food and water, while others, such as radon, are inhaled. So you can see in normal day-to-day life also. Normally, some products having low level of uranium and thorium and the decay products are ingested with food also, with water also, and radon like are also inhaled. So you can see the radiation in the nearby areas also. The dose from terrestrial sources varies in different parts of the world. Locations with higher concentration of uranium and thorium in the soil have high dose levels. Okay, now we are talking about humans. All people also have radioactive isotopes such as potassium 40 and carbon 14 inside their bodies. Okay, these variation in dose, the variation of this two that they are talking about, those vary from one person to another. It's not as great as the variation in dose from cosmic and terrestrial sources. Okay. There are also a number of man-made radiation sources that present some exposure to the public. Some of these sources include tobacco, television, sets, smoke detectors, combustible fuels, certain building materials, nuclear fuels for energy production, nuclear weapons, medical and dental X-rays that they use for diagnostic purpose, nuclear medicines, X-ray security systems, and industrial radiography. You can see this radiography has vast applications. It is applicable in various, you can say, facilities of the world, like big smoke detectors, building materials, and nuclear plants that we know nuclear fuel for energy production. So they have an application. Okay, by far the most significant source of man-made radiation exposure to the average person is from medical procedure. Okay, such as diagnostic X-rays, nuclear medicines, and radiation therapy. Okay, so this is one of the most prominent and significant source of man-made radiation. Okay. Now the measures related to the biological effects of radiation exposure. So normally we say that there are four measures of radiation that radiographers will commonly encounter while addressing the biological effects of working with X-rays or gamma rays. Now those four measures are like exposure, dose, dose equivalent, and dose rate. Okay, we will discuss all these four measures one by one in the coming slides because these are important to understand. Okay, now exposure. We have understood this term earlier also, exposure, and here we are doing it once again because it is a math because this is a very important topic. Sorry. Now, exposure is a measure of the strength of a radiation field at some point in air. The amount of charge produced in a unit mass of air when the interacting photons are completely absorbed in that mass. Okay, now this is a measure made by radiation surveymeters since it can be easily and directly measured. The most commonly used unit of exposure is the Roentgen. We have studied about this Roentgen unit earlier also. Okay, now dose or absorbed dose. Okay, while exposure, while exposure in defining for air, that is now dose or absorbed dose, while exposure is defined for air, the absorbed dose is the amount of energy that ionizing radiation imparts to a given mass of matter. Okay, absorbed dose is the amount of energy that ionizing radiation imparts to a given mass of matter. You can say another way also that it is the amount of radiation absorbed by an object. The SI unit for absorbed dose is gray, short named as GY, gray. Okay, GY. But the RAD, radiation absorbed dose, RAD, you have to remember this term also, RAD, radiation absorbed dose, GY gray, is commonly used. Okay, because 1 gray is equals to 100 rad. Rad is radiation absorbed dose. So you can understand that radiation is also used in, sorry, RAD, rad term is also used and gray term is also used. And 1 gray is equals to 100 rad. Okay. Now different materials that receive the same exposure may not absorb the same amount of radiation. In human tissue, one Roentgen of X-ray or gamma radiation exposure results in about 1 rad of absorbed dose. You can understand that how the exposure was expressed in terms of Roentgen just now, one Roentgen of X-ray or gamma radiation. In the previous just studied, no, that exposure is expressed in Roentgen. So one Roentgen of X-ray or gamma radiation exposure results in about 1 rad of exposed dose, sorry, absorbed dose. So how in units term they are explaining the practicality of that uh, exposure and absorbed dose. The size of the absorbed dose is dependent upon the intensity or activity of the radiation source. Okay, now there are some factors on which this absorbed dose is dependent. Okay, you have to consider these also. The size of the absorbed dose is dependent upon the intensity or activity of the radiation source, the distance from the source, and the time of exposure to the radiation. Okay, intensity is valuable, distance from the source is also important, and the time of exposure of radiation. Okay, so in by having all these factors, you can have the size of absorbed dose with you. Now dose equivalent. The dose equivalent, it relates to the absorbed dose to the biological effect of this dose. Okay, absorbed dose to the biological effect of this dose. The absorbed dose of specific types of radiation is multiplied by a quality factor to arrive at the equivalent dose at a dose equivalent. Okay. Now the SI unit is the SV, sievert, SV, sievert. But the REM, Roentgen equivalent in man, REM, Roentgen equivalent in man, is commonly used. And 1 SV is equals to 100 rem. In previous the absorbed dose it was one gray is equals to 100 rad. Now it's in dose equivalent it is 1 SV is equals to 100 gram. Each of the measure has its own units of measurement. Now the table below presents the Q factor. Q is quality factor for several types of radiation. Like for X-ray, there are types of radiations are there like X-ray, gamma ray, sorry, beta particles, thermal neutrons, fast neutrons, alpha particles, sorry. And in terms of RAD, that is the absorbed dose, it is showing their values in quality factor, it is showing their values, and the RAM, it is showing. Okay. Now the X-ray has one rad and quality factor of 1, and so REM is equals to 1. Then gamma ray has equivalent their values, beta particles have their values, thermal neutrons have quite different values because the quality factor is different, it is 1. Okay, sorry, one quality factor is 5, so REM is equals to 5. Then fast neutrons, they have 10 as a quality factor, so the REM is also 10 in that one. Alpha particles have one rad only, but their quality factor is 20, so you can imagine the quality factor. So 20 is the REM. Dose rate, the final measure that needs to be understood. The dose rate is the measure of how fast a radiation dose is being received. Dose rate is usually represented in terms of MR by HR, okay, or MREM by HR, or radiation per minute, or mgray into mgray per second, etc. Okay, knowing the dose rate allows the dose to be calculated for a period of time. So we have to understood dose rate also. It is a measure of how fast a radiation dose is being received. As the name says, dose rate. How fast a radiation dose is being received. Okay, so it's measured in mgray per second. Very easy to use. Now controlling radiation exposure. When working with radiation, there is a concern for two types of exposure. Normally, they find out with the past experimentation in the past, they find out that while working, there is concern for two types of exposure that we have find out. One is acute and one is chronic. So we are discussing about these two. An acute exposure is a single accidental exposure to a high dose of radiation during a short period of time. An acute exposure has the potential for producing both non-stochastic and stochastic effects. Okay, so this is also important because acute, the word says acute exposure means for short duration of time. So exposure to a high dose of radiation during a short period of time is acute exposure. Now chronic exposure. So it is also called as continuous exposure. Is a long term, low level overexposure. You can see the words what they are saying. Also called as continuous exposure. So it is for a longer time. So it is a long term exposure. with low level overexposure. Okay. Now, chronic exposure may result in stochastic health effects and is likely to be the result of improper or inadequate protective measures. So, this is the negligence. Okay, negligence of not using protective measures. That's why it's continuous exposure also. Another name is continuous exposure. Okay, so this is chronic exposures are a result of inadequate protective measures or improper protective measures. So you can go with that also. Now, three basic ways of controlling exposure to harmful radiations are like they have shown you in this three figures also on the bottom. That time, the less time spent near source, less radiation received. Very truly said. Okay. Then distance. Greater distance from source, less radiation received. This is also true. Okay. And shielding. Behind shielding from source, less radiation received. So these are the common ways. These are the common basic ways of controlling exposure to harmful radiation. Okay. And these are very well defined and expressed in these diagrams also. Okay. Like the first is limiting the time spent near the radiation source. It is shown in the first diagram also. Then second is increasing the distance away from the source. Very truly depicted in the second diagram in between. Then using shielding to stop or reduce the level of radiation. This is also shown in the third diagram. Very well. Now time. We are discussing all these things in you can say in detail. The radiation dose is directly proportional to the time spent in radiation. Right. The more time you spend, then the more radiation is there for you to face. Therefore, a person should not stay near the source of radiation any longer than necessary. If it is not required, you should not stay there. If a survey meter reads 4 mR/h at a particular location, a total dose of 4 mR will be received if a person remains at that location for 1 hour. Okay, for 1 hour you will receive this kind of dose. So the received dose can be simply calculated as dose equals to dose rate into time that we just did in the previous slides. So when using a gamma camera, it is important to get the source from the shielded camera to the collimator. Now, what is collimator? Collimator is a device that shields radiation in some directions but allows it to pass in one or more other directions. Okay, so it is important to get the source from the shielded camera to the collimator as quickly as possible to limit the time of exposure to the unshielded source. Okay, so in this way, you can avoid your time spent in the radiation. You can go by using a gamma camera, so for where you can find the source, okay, and limit the time of exposure to the unshielded source. Okay, now distance. Increasing distance from the source of radiation will reduce the amount of radiation received. That is also true. If you can not disturb the time, then you can do with the distance also. That you can increase the distance from the radiation of source. Okay, increase the distance from radiation source will reduce the amount of radiation received. As radiation travels from source, its spread out becomes less intense. Okay, the radiation will start from the source. So when it's spreading out, it will become less intense. This phenomenon can be expressed by the Newton's inverse law. We have discussed this inverse law before also, which states that the radiation travels out from the source. The dosage decreases inversely with the square of the distances. Like I1 upon I2 is equals to D2 square upon D1 square. This we have discussed in the previous you can say lectures also. Is Newton's inverse square law. Now shielding. The third way to reduce exposure to radiation is to place something between the radiographer and the source of radiation. Very true. Now, in general, the more dense the material, the more shielding it will provide. Okay. Now, lead and concrete are the two commonly used radiation shielding materials, primarily because they are easy to work with and are readily available materials. We have studied about previous also that how lead has been used as a shielding material and what applications does it have in radiographic testing. How concrete has given its contribution as a shielding material. So when you talk about shielding, then if you want to reduce the exposure to radiation, that is, you have to put a shield between the radiographer and the source of radiation. So lead and concrete, they are the most commonly used materials as they are easily available materials also. Concrete is commonly used in construction with radiation walls. Some walls will also be lined with lead. See how they are applying these two materials to reduce the exposure to radiation. Okay, some walls are also lined with lead sheeting to help reduce the radiation to acceptable levels on the outside. Okay, so this is a kind of an application also. You can see in the right hand side also a diagram is showing of a vault and what message does it is displaying on the front for others to read. Okay, exposure limits. Over the years, numerous recommendations regarding occupational exposure limits have been developed by international radiation safety commission. Now, in general, the guidance established by the radiation exposure have two principles of objective. Now, we have studied about two kinds of the acute exposure and chronic exposure. Now, they are discussing about that one. To prevent acute exposure, okay, and then to limit chronic exposure to acceptable limits. Okay. Now, current guidelines are based on conservative assumptions that there is no safe level of exposure. So this assumption has led to the general philosophy of not only keeping exposure below the recommended level or regulating limits, but also maintaining all exposure as low as reasonable achievable. See, these term as low as reasonable achievable, this is a very common term and they say as there is no safe level of exposure. So depending upon the past experiences or past experimentations, they have to find out the you can say exposure levels. They have to find out the regulation limits. Okay, or you can say you have to find out they can go for recommended levels for which you can say go for the exposure. So they follow the term ALARA. ALARA means as to as reasonable achievement. ALARA is a basic requirement of current radiation safety practices. It means that every reasonable effort must be made to keep the doors to workers and the public as far as the required limits as possible. Okay, so you can go with the as low as reasonable achievable ALARA. Okay, it is a kind of a radiation safety practice. Okay, which is keeping the workers and the public, okay, they are in the limits only as far as below the limits as possible. Now in general, most international radiation safety tools specify that dose rate must not exceed 2 mr by hour per hour in any unrestricted area. Okay, the specifications for the accumulated dose per year differ between radiation workers and non-workers because see there are people who are working with radiographic testing and there are people who are not working. So there are particular limits for each of them. Okay. So regulatory limits for occupational exposure. Okay. Most international codes set the annual limit of exposure for industrial radiographs, who generally are not concerned with the intake of radioactive material as such. Okay, the more limiting of, or you can say the total effective dose equivalent of 5 REM, that is 0.05 SU. We studied about this in previous years. So you can see in the diagram also the total effective dose equivalent, whole body, it has given a 5 REM, that is 0.05 SU. Now I dose equivalent is equal to 15 REM, that is 0.15 SU. Then the if you come to the around the neck region, then it will give you shallow dose equivalent whole body skin that is 50 REM. or you can say 0.5 SC. Then it has gone to the organ dose. Then total organ dose equivalent, any organ that is having 50 RPM, that is zero point 0.5. And if you talk about the whole body equivalent, then it goes to 5 RPM, that is 0.5, 0.05. So you can say that the sum of the deep dose equivalent to any equivalent organ or tissue other than the length of the eye being equal to 50 RPM, that is zero point 0.5. The annual limits to the length of the eye, to the skin, and to the extremities, which are lens dose equivalent to 15 REM, that we show in the figure also, that is zero point 0.5 SV. A shadow dose equivalent to 50 REM, the skin or any extremity that you have seen in the diagram also. So they have limits, okay, for occupational exposure also. So these are annual limits of exposure, okay, but these are for industrial radiographers. The shallow dose equivalent, okay, is the external dose. Shallow dose equivalent you have seen in the diagram on the bottom side it is written there. Shallow dose or in between the two doses it is written shallow dose equivalent. You can see in the diagram also. So this is an external dose to the skin of the whole body or extremities from an external source of ionizing radiation. Okay, this is an external dose to the skin of the whole body or extremities from an external source of ionizing radiation. The value of the dose equivalent to at a tissue depth of 0.007 centimeters, averaged over an area of 10 centimeters square. So you can see that this has a value. Okay, this has a value also. Now the lens dose equivalent is the dose equivalent to the length of the eye from external source of ionizing radiation. Now this value is the dose equivalent at an tissue depth of 0.03 centimeters. The deep dose equivalent is the whole body, okay, dose from an external source of ionizing radiation. And this value is dose equivalent at a tissue depth of 1 centimeter. So you can see the tissue depth from shallow dose that is also having 0.007 centimeter. Then in the lens dose it went to zero point 0.3 centimeter. Then in the deep dose this went to 1 centimeter. Okay. Now the total effective dose equivalent is the dose equivalent to the whole body. Okay, the whole body. Now declared pregnant workers and minors, for them, what are these limits? Because of the increased risk of to the rapidly developing embryo and fetus, pregnant women can receive no more than zero point 0.5 REM during the entire gestation period. Okay, this is only a 10% of the dose limit that normally applies to the radiation workers. Only 10% because to give 5 REM for all workers. But for pregnant women, you should go with zero point 0.5 REM only. That is 10% of the dose limit. The same limit also applies to person under the age of 18 years old. So they can go with only 10% of the dose limit. Now, non-radiation workers and the general public. The dose limit to non-radiation workers and members of the public is only 2% of the annual occupational dose limit. Therefore, our non-radiation workers can receive a whole body dose of no more than 0.1 REM per year. Can you understand? 0.1 REM per year from industrial ionizing radiation. Okay, they can receive 5 REM. The workers, then it went to the pregnant women, it goes to zero point 0.5 REM. Then the general public or non-radiation workers, we can go with zero point 0.1 REM per year. So this exposure would be in addition to the zero point 0.3 REM per year from natural background radiation and the 0.05 REM per year from man-made sources such as medical effluents. Okay. Then overdose health symptoms. Now there are when you go for an overdose, there are some symptoms also. These symptoms will be known to you. So listed are some of the probable prompts and delayed effects of certain doses of radiation when the doses are received by an individual within a 24-hour period. Okay. Now if there is so if you go with the to 25 REM, then no injury evident is there. First detectable blood change at 5 REM. Then 25 to 50 REM, Definite blood change at 25 rem, no serious injury. At 50 to 100 rem, then some injury is possible. At 100 to 200 rem, it will go to injury and possible disability. Then 200 to 400 rem, it will go with injury and disability, likely death possible. Then 400 to 500 rem, you can see how it is increasing. Then median lethal dose, 50% of exposure are fatal. Now it's becoming serious. Now 500 to 1000 rem, up to 100% exposure are fatal. Then over 1000 rem, 100% likely fatal. So as soon as the value is increasing, the you can say the risk, the fatality is increasing again and again, more and more and more. Okay, it is leading to somewhere it is into this injury, the injury to disability, then death. If not death, then fatal positions are happening. The delayed effects of radiation may be due to either to a single large overexposure or continuing the low levels of exposure. Now, example dosages from you can say resulting symptoms when an individual receives an exposure to the whole body within 24-hour periods. Like if you go with 100 to 200 rem, they give you us an example from the data that they have found out during the experimentation process. So if you have exposure of 100 to 200 rem, sorry, not rpm, rem, 100 to 200 rem, then in the first day they will feel that no definite symptom. Then first week no symptom. Second week also no symptom. Third week loss of appetite, malaise, sore throat, and diarrhea. So now you are able to find out that there are some symptoms due to the exposure to the whole body. Okay. Now this is somewhat like a kind of serious discussion. In the fourth week, recovery is likely in a few months unless complications develop because of poor health. If there is low immunity, then due to overexposure, the recovery will not be possible. So it is if the health is very less or it has low immunity, then recovery will be you can say a bit slow down. Okay. Now they are giving the example of a higher number that is 400 to 500 rpm. Then for this, if you are the first day, you will feel that something is wrong, like nausea, vomiting, diarrhea, usually in the first few hours only. Then first week, symptoms may continue. Second week, then elevation, loss of appetite. Third week, hemorrhage, nosebleeds, inflammation of mouth and throat, diarrhea, emaciation. Then fourth week, rapid emaciation and mortality rate around 50%. So you can see that how this exposure can be harmful, how this overexposure can be harmful. Okay, how this chronic exposure can be harmful. So we should avoid such a kind of. Then there are radiation detectors. Okay, there are radiation detectors. These detectors are also useful. Now we'll study about these also. Instrument used for radiation measurements fall into two broad categories. One is the rate measuring instruments and the personal dose measuring instruments. Now, rate measuring instruments means they measure the rate at which the exposure is received. So, more commonly called as the radiation intensity. Okay. Now, the survey meters, audible alarms, area monitors, they fall into this category. There are some, you can say, the instruments that are used, like survey meters, audible alarms, area monitors, they fall into this category, that rate measuring instruments. So, these instruments, they present a radiation intensity reading related to time, that is R per hour. Okay, radiation intensity reading related to time, or MR per HR or per hour, sorry. An analogy can be made between the instruments and the speedometer of a car because both are measuring units related to time. Okay. Now dose measuring instruments. Earlier was rate measuring instruments. Now it's dose measuring instruments like dose rate and absorb dose. So we should be aware of these also. You can see in the diagram also how these instruments look like. Now, dose measuring instruments are those that measure the total amount of exposure received during a measuring period. The dose measuring instruments or dosimeters that are commonly used in industrial radiography are small devices which are designed to be worn by an individual to measure the exposure received by the individual. Okay, now these instruments, commonly known as dosimeters, okay, they are normally given to people who are involved in radiography in the industry. Okay. Now these instruments are not big instruments. These are small instruments. Okay, that can be kept with the concerned person, with the worker, with himself or herself only. They are actually worn by the individuals. Now, why they are doing this? Because this is worn by the individual to measure the exposure that they are receiving. Okay, so an analogy can be made between instruments and the odometer of a car that are both used for measuring accumulated limits. So you can understand that how industry radiography is careful and managing the exposures of their employees, of their workers to keep them safe. Now survey meters, these are some instruments that are used. The survey meter is the most important source a radiographer has to determine the presence and intensity of radiation. Okay. Now there are many models of survey meters able to measure radiation in the field. One of these you can see in the right hand the diagram also. They all basically consist of a detector and a readout display. See, if you talk about meter, then there had to be a display and consist of a detector. Obviously, the purpose is to determine the presence and intensity of radiation. So there needs to be a detector. The basic principle of a submitter is to determine the presence and intensity of radiation. So there need to be a detector and a display to read out the readings. So analog and digital display are available. Okay. Most of survey meters used for industrial radiography use a gas filled detector. Okay. Now this is one of the important, we can say, source that normally radiographer, industry radiographer has. Now gas filled detectors. Now these consist of a gas filled cylinder with two electrodes having a voltage applied to them. This consists of a gas filled cylinder with two electrodes having a voltage applied to them. So whenever a device is brought near radioactive substances, the gas becomes ionized. When a device is brought near radioactive substances, the gas which is filled inside, it becomes ionized. Now the electric field created by the potential difference between the anode and the cathode, the electric field created by the potential difference between the anode and the cathode causes the electrons of each ion pair to move to the anode while the positivity charged gas atoms is drawn to the cathode. See, now here the technical thing. What they are saying, the gas becomes ionized when these ejectors come near radioactive substances. Now what happens? The electric field created by the potential difference between the anode and the cathode causes the electrons of each ion pair to move to the anode. Now the electrons are moving to anode, while the positively charged gas atoms are drawn to the cathode. Electrons are going to the anode, and the positively charged gas atoms are going to the cathode. Now this results in an electrical signal that is amplified, correlated to exposure, and displayed as a value. The more the electrons go to the anode and more the positive charged gas atom goes to the cathode, the more the value is. So here you can see how the gas is being used to find out the value. Okay. Now audible alarm rate meters. Now this is also very important topic. As you can see in the diagram, there are some alarms that are being used. The audible alarm, these are devices that emit a short beep or a chirp. So you can see the uh, birds chirping when a predetermined exposure has been received. Now, this is somewhat really a very important instrument. Audible alarms, okay, they give you a beep or chip when a predetermined exposure has been received. So you can see on the diagram also there is some on off push button showing the battery auto check right before manual operating. So there is a rate alarm written on the bottom side. So understand that this is somewhat an instrument that is going for rate alarm. So it is required that these electronic devices be worn by an individual working with gamma emitters. Now this is a variable device. You can keep it uh, in the pocket or in the bottom side of the belt. Now, these devices these reduce the likelihood of accidental exposure in industrial radiography by alerting the radiographer to expose to the levels or dosages of radiation above a present amount. Okay. Now, these devices, what they do, they alert the radiographer. Okay. The person who is working in the industry as a radiographer, they alert the radiographer to exposure levels or dosages of radiation above a present preset amount. Okay, there is an exposure that they know, but they are being alerted about the exposure levels with the help of these rate alarms. Okay, it is important to note that the audible alarms are not intended to be and should not be used as replacement for survey meters. Modern survey meters have this alarm feature already built in. Survey meters have their own application, rate alarms have their own application. Okay, but now a combination of both survey meters and alarm, they are already being used right now. Now let's go with our, you can say, quiz. Okay, now the major isotope of concern for terrestrial radiation are, which are the common, you can say, uranium and decay products of uranium, such as thorium, radium, and radon. We all know that we have studied in previous slides also that the major isotopes of concern are like uranium and decay products of uranium. So it is true. Then exposure is a measure of the strength of a radiation field at some point in air. The amount of charge produced in a unit mass of air when the interacting photons are completely absorbed in that mass. See, we are studying about this exposure from previous, you can say, lectures also, and we know that the importance of exposure and how it is measured. So here it is saying that exposure is a measure of strength of a radiation field at some point in the air that we know. That is the amount of charge produced in a unit mass of air when the interacting photons are completely absorbed in that mass. That is the exposure. So it is true. Now the dash is a measure of how fast a radiation dose is being received. Okay, we have studied about this also that uh, how fast is it? What do we call this? We call it as dose rate. Okay. Now there is discussion about acute exposure. Okay. An acute exposure is a single accidental exposure to a high dose of radiation during a short period of time. See, this is a very important like exposure because you can say for a short period of time it has a very high impact. So what do you call this? This is either true or false. Then acute exposure is a single accidental exposure to a high dose of radiation during a short period of time. What do you call this? Is true or false? To a high dose of radiation during a short period of time. It's true. Now the basic way of controlling exposure to harmful radiation are now here you are discussing about the basic ways of exposure. Now that we have discussed all of these like limiting the time spent near the source of radiation, then increasing the distance away from the source, then using shielding to stop or reduce the level of radiation. We studied about lead and concrete used as a shielding material. Okay, so the answer is all of these. All these, the above three ways are important in controlling exposure of to harmful radiation. Okay, in these all are important. Now, sixth question is the dash is directly proportional to the time spent in the radiation. The received dose can be simply calculated as dose equals to dose into time. This is simple radiation dose. Very simple as the you can say statement says radiation dose. Now increasing distance from the source of radiation. Right. Increasing distance from the source of radiation will reduce the amount of radiation received. What do you call this? I repeat, increasing distance from the source of radiation will reduce the amount of radiation received. We have discussed about the, we can say the things which needs to be uh, considered while keeping you safe from the exposure. This is one of the things, increasing distance from the source of radiation. So it is true. Now the eighth question, it is the most commonly used radiation shielding material, primarily because they are easy to work with and are readily available. I just told you right now, lead and concrete, these both are the common radiation shielding materials, primarily because they are easily available and they are easy to work with. Okay, then next question, the dash is the external dose. The dash is the external dose to the skin of the whole body or extremities from an external source of ionizing radiation. Now this is also very important, and this we have studied that is called a shallow dose equivalent. There was a diagram shown for the human body, and it was shown all these dose equivalents. So from that you can understand that shallow dose equivalent, lens dose, deep dose. Now the dash is the dose equivalent to the length of the eye from an external source of ionizing radiation. What do you call this? Either shallow dose or lens dose or deep dose or none. We will go with the lens dose. Lens dose. So we have completed our MCQs for today, and these are the references that you can discuss or with me, or if possible you can read them if possible, because these references are a source of knowledge which you and while reading this you can enhance your knowledge in the respective topics. Okay, these references will give you you can say good backgrounds also, which will make your study interactive and will update your knowledge also. So I hope you all enjoyed the session. So this is all for now. Thank you. Thank you all.